Hey everyone, going to section 12.3, going to talk about velocity and acceleration. So to start off, one of the big applications of differentiation and integration that you learned back in Cal 1 mostly, but a little bit in Cal 2 as well, is motion. So in Cal 1, you learned about a motion along a line, right? So if you only have one direction, you can go forward, you can go backwards. You learned about the relationship between position, velocity, acceleration. And then when you learned about parametrics in Cal 2, you could extend that to motion along some kind of a curve in a two-dimensional plane. Now that we know about vector valued functions, we can extend this to pretty much any amount of dimensions. But for the sake of reality, we'll stick to 2 and 3 dimensions. So big thing that you've learned is that if you start off with position and you take the derivative, you get velocity. If you take the derivative again, you get acceleration. And one of the most important things to remember is in physics, which is one of the uh, main areas of study that applies calculus, acceleration is pretty important because force is mass times acceleration, right? So we're going to talk a lot about that in this section and the next 2 sections as well, really more so 12.5. But it's important for us to understand this relationship. And if I wanted to go backwards, I could use integration. All right, so other than that, just remember with vector valued functions, any calculus that you do is done component wise. And if you ever want to find the magnitude of a vector, you know a formula for that. Okay, so let's just do some examples. First one, we want to find the velocity vector, the speed, and the acceleration vector for a particle that moves along the plane curve C given by that vector valued function. So this is our position. If I want to find the velocity vector for part A, I just need to find the derivative of my position vector. So if I take derivative of sine of t over 2, that's going to be cosine of t over 2 multiplied by 1/2 chain rule. Since I already have the 2 there, 1/2 times 2 will just give me cosine of t over 2. And that's going to be the I component. For the next part, 2 cosine of t over 2. Derivative of cosine is negative sine. Derivative of t over 2 again is 1/2. Since I already have a 2 there, this will be minus sine of t over 2 j. And this is my velocity vector. Now for part B, I want to find the speed of the particle. So speed, remember, is the magnitude of velocity. So essentially, we want to find the magnitude of r prime, all right, which we can get from our extended Pythagorean theorem. So that's going to be cosine squared of t over 2 plus negative sine of t over 2, all of that squared. And we end up getting cosine squared t over 2 plus sine squared t over 2. So we have the same argument. We have sine squared plus cosine squared. We know that that's going to be 1. So the speed of this particle is constant and has a value of 1. And then for part C, we want to find the acceleration vector, which means that we need to take the second derivative. So we want to find r double prime of t. So derivative of cosine, we get negative sine. Derivative of the inside is 1/2. Derivative of negative sine is negative cosine. Derivative of t over 2 is still a half. And that is my acceleration vector. And that's part A, part B, part C. Okay. For the next example, we want to sketch the path of an object that's moving along the plane curve given by this vector valued function. We want to find the velocity and acceleration vectors for two different values of t. So if I want to sketch this path, easy way for me to do that is to kind of make a little table. So I'll have values of t that I can use. I'll have x coordinates that I get, which are going to correspond to the I component, and y coordinates that I get, which will correspond to the j component. So if I look at this, we're looking at the velocity and the acceleration when t is 0 and when t is 2. So one thing I can do is just choose values of t that go between 0 and 2. So if I plug 0 in for t, for my x component, I end up getting 0 minus 4. So that's an x coordinate of negative 4. And for my y component, I just get 0. For my coordinate when t is 1, x coordinate we get 1 minus 4, negative 3. Y coordinate we get 1. And then when t is 2, 4 minus 4, I get 0. And 2 for my y coordinate. So I can plot these points to kind of get an idea of where the coordinate is at these different values of t, right? Another thing I can do to kind of figure out what the general shape is going to be is look at these as parametric equations. I know that y is equal to t, right? Because that's our j component. I know that x, so our I component, is equal to t squared minus 4. But remember, what is t? T is y. So we end up getting a sideways parabola. So if I were to sketch this, right, this would be the point when t is equal to 0. Okay. Then when t is equal to 1, we would go negative 3, positive 1, and 0, 2. So between t equals 0 and t equals 2, we're basically moving from this point to this point. And remember, with vector valued and parametrics, we want to have arrows that show us the direction that the object's moving. And we know that this is going to continue off as t gets larger than 2. To have a complete picture of the path, though, because it didn't really say to only sketch this part of it, we know that this is going to be a sideways parabola because of the shape of this equation. So I know that we're going to have symmetric points, which will end up looking like this. And these would correspond, these would correspond to negative values of t. So essentially, we're moving along this parabola in this direction. This is when t is 0, this is when t is 2. So we've sketched the path. The next thing we look at is to find the velocity and acceleration vectors. So velocity, often denoted by v of t, is going to be the derivative of my position vector r. So derivative of this component will just be 2t. So we have 2ti. Derivative of t would be 1. So 2ti plus j. And that's our velocity vector. This is our sketch. Label x, label y. Oh. And then our acceleration vector we can get by taking our second derivative. So derivative of 2t is just 2, so we get 2i. Derivative of 1 is 0, so the acceleration does not have a j component. And there we go. That's the next example. All right, moving on. Let's say that we want to sketch the path of an object moving along a space curve. So now we're extending to 3 dimensions, and we have these 3 components. And we're also given that t is greater than or equal to 0. So before we had to draw an entire path out for positive and negative values of t. Here we're only going to consider positive. And then we want to find the velocity and acceleration vectors when t is equal to 1. Oh, whoops. Got to do that for these. Yep. So, yeah, backtracking. So if I want to find the velocity vector when t is 0, I just plug in 0 for t, and I get 0 for my I component, and I still have 1 for the j component. If I want to find my velocity vector when t is 2, same idea. Plug 2 in for t, I get 4i plus j. Now for the acceleration vectors, acceleration when time is 0 is still going to be 2i. There's no t for me to plug into, that's constant. So no matter what value of t we take on, the acceleration will always be the vector 2i. There we go. And now we can go back to this one. All right, so first let's start off by sketching. So we know that we can write our equations in terms of parametrics. So I know x, that's the I component, is equal to t, which means my y component is equal to t cubed, meaning y is equal to x cubed. And if I were to take it further, I could also say that z is equal to 3x. So if I were looking at the xy coordinate, I would get, yeah. If I were looking at the xy coordinate, I would get a coordinate plane. I would get a graph like y equals x cubed. That's our cubic function that looks kind of like this if you draw it on just a regular xy plane. And then if you look at the z component, right, z is equal to 3 times x. So if we wanted to, we could start off with t equals 0. Remember, we'll label our axes, x, y, and z. So when t is equal to 0, x is equal to 0. And we can kind of make a similar table to like what we did last time, except this time we have an x, we have a y, and we have a z. So because this starts with t equals 0, that's where I'm going to start. So we'll have an x coordinate of 0, x cubed would still be 0, and 3 times x would still be 0. So I know that the origin is where this path starts when t is equal to 0. If I were to continue, let's say t is 1, that means x coordinate is 1, the y coordinate is 1, the z coordinate is 3. And if I were to go up more, if t is equal to 2, x is 2, y is 2 to the third, or 8, and z is 3 times 2, 6. So essentially, we're drawing out the first quadrant part of the x cubed graph, right? Because we're not going to consider negative values of x. And this is rising at a rate of 3 for every change of 1 in x. So if I start off, we have our point 1, 1, 3. So over 1, shoop, shoop, and then up 3, which will put us about right there. So we go from here out through there. Remember, this makes kind of like in 2 dimensions, it makes kind of like this kind of shape, right? But imagine this just slanted upward. Then when y is 8, x is 2, z is 6. We end up at that point. So we're just continuing that shape. So again, it's like if you take this guy and kind of pull it up, keeping the origin on the paper. Yep. And again, we want to indicate direction here. We know that this would continue past that if t were to move past 2. So this is our sketch. Next, we want to find our velocity and acceleration vectors for a particular value of t. So velocity vector v is the derivative of the position vector r. So we get 1I, so just I, 3t squared j, 3k. And if I wanted to find the velocity when t is equal to 1, I would get I. Remember, there's no t there, so that's just going to be 1I, no matter what time, or no matter what the value of t is. If I plug 1 in for t here, I get 3j and 3k. So that's my velocity vector when t is equal to 1. Side note, if I wanted to find the speed of the object when t is 1, how would I do that? I'd basically get this vector and then I would find its magnitude. We weren't asked for that, but just an opportunity to test your knowledge. All right, and then the acceleration vector, we take the second derivative of our position vector. So derivative of 1 is 0, so there's no I component. Derivative of 3t squared is 6t, so we get 6tj. The derivative of 3 is 0, so our acceleration has no k component either. So the acceleration vector is 6tj. And if I wanted to find the acceleration vector when t is equal to 1, I would just plug 1 in for this t here, and I would get 6j. So the acceleration is only in the y direction. Meaning if you had a force acting on this object, it would only be acting in this direction. All right. Next example, we have an object that starts from rest at this coordinate and moves with an acceleration given by this vector. And it tells us that the magnitude of the acceleration is measured in feet per second per second. The purpose of bringing up those units is so that you know distance is in feet and time is in seconds. We want to find the location of the object after t equals 2 seconds. All right, so basically this is our position to start with. So I think of this as r of 0. If I want to find position or location and I start off with acceleration, I have to integrate twice. So remember, the first time I integrate, I'm going to get my velocity vector. So the integral of the acceleration vector with respect to t. So since there is no I component, right, we know that the velocity could have had an I component that was just a constant. So I'm going to say C1I j. If I take the integral of 1 dt, I get t plus a constant we'll call C2j. And then oh. And then if I take the integral of 2, I get 2t plus a constant C3k. Now, another piece of information we were given here that may not seem very obvious at first is that we were told the object starts from rest. What that means is that the initial velocity is equal to zero, the zero vector. Right, so keeping that in mind, I know that if I were to plug zero in for every value of t, it's C1i plus C2j plus C3k, right? Because that's zero, 2 times t is zero. Yeah. We know that this gives us the vector 0i plus 0j plus 0k, which means that all of these constants of integration that we got were equal to zero. So the velocity vector will not have an I component. T would be the J component, and 2t would be the K component. Now, if I want to get my position vector, I have to take the integral of the velocity vector. So that's going to give me, again, another constant. I'll call C4 plus, and then I take my integral for t, that's going to be t squared over 2 plus a constant, we'll call C5. Oops, that should have an I. Yep. You need your parentheses here because there's more than one term. And for 2t, the antiderivative is t squared plus another constant. So at this point, I can use the starting coordinate to figure out what these constants are. All right, so I know that C4 based on this has to be equal to 1 because the y coordinate, or because the x coordinate of the starting point is 1. For the y coordinate, we know that t squared over 2 plus C5, right? This is our y coordinate, is equal to 2. And then, oh, whoops. This is specifically when t is equal to 0. So instead of writing t squared, I'm actually just going to plug 0 in for that. So that tells me that C5 is equal to 2. Now for the z coordinate, we get 0 squared plus C6 is equal to the z coordinate we were given, which was 0, which tells me that C6 is equal to 0. So altogether, I know that the coordinate r of t for any value of t is given by the vector I plus t squared over 2 plus 2j plus t squared k. Now, the question asked us to find the position of the object when t was equal to 2. So for I, it's still going to be I. There's no t dependence here. For j, if I plug 2 in for t, I get 4 over 2. That's 2. Add 2, you get 4j. And then 2 squared, we get 4k. So that's the position vector, meaning that we would be at the coordinate 1, 4, 4. And there we go.